Hey, all you cool cats and kittens. Welcome to the beginning of Unit 4 over Analytical Trigonometry. Cannot wait to start this. So much fun. It's all about fundamental trigonomic identities. That's what we're going to learn about in this video. We're actually not going to really do any problems in this video. This problem is really just kind of an introduction to what the fundamental trigonomic identities are. And the next bunch of videos are going to be utilizing the fundamental trigonomic identities. So fundamental means that these are like the beginning, the foundation, the building blocks of all other trigonomic identities, the main ones, right? So there's millions, there's lots of trigonomic identities out there. These are the building blocks, the main ones. But the other thing is, what the heck's an identity? I hope by now you guys get trigonometry, sine, cosine, tangent, all that fun stuff. But let's talk about what an identity is real quick, because you're not going to understand any of this until you truly understand what an identity is. So let's talk about the equal sign. In the math, the symbol equals, the two parallel lines, means several different things. In basic arithmetic, it means 1 + 1 = 2, right? This is just an equality of real numbers. It means if we understand this concept of addition, if we take 1 + 1, we get this new number 2, right? It's just equality of numbers. That's one very simple thing that we understand. It's just a true mathematical sentence. But another example is an equation, where we have something like an x, a variable, right? And here we have cosine of x = 1/2. This is really more of an open sentence. And I mean open because it can be true or false, all depending on what x is. You know, in trig functions, the input x represents an angle. And not every angle is going to make this a true statement. There are actually infinite answers to this, but not every angle is an answer. You know, if I plug in 90 degrees, cosine of 90 degrees is 0, not 1/2. So 90 degrees is not a solution. If I plug in 9 degrees, it is not going to be true. So I say it's an open sentence because it all depends. Sometimes it's true, sometimes it's not true. And that's really the foundation of an equation. And we like to solve equations to figure out what the solutions are. So that's a different use of the word equals. But an identity uses an equal sign in a really different way. So an identity is an equality that holds true regardless of the values chosen for its variables. A really simple one in terms of algebra is x times 0 = 0. That is an identity because you could plug in anything you want for x, as long as it's in the domain, as long as you're allowed to plug it in. Plug in anything you want for x. 2, 3, 5, 1/2, 90 degrees, pi/2. I don't care if you plug, radians and degrees are numbers. So again, plug in any number you want for x and you're going to get a true statement. Let me give you another identity. Again, identity is an inequality, or it's an equality. So it's got to be an equal sign. And it's going to hold true no matter the variables you choose. So here's another one. X divided by x = 1. That is an identity, because it doesn't matter what values for x you plug in, as long as they're in the domain. Oops, sorry about that. So as long as you don't plug in 0, because obviously 0 divided by 0 is meaningless. 0 divided by 0 doesn't even make sense mathematically. So as long as you're in the domain, so all numbers other than x, it doesn't matter. 5 divided by 5, 1. 6 divided by 6, 1. Pi/2 divided by pi/2, 1. 90 degrees divided by 90 degrees, 1. 180 degrees divided by 180 degrees, 1. That's an identity. Again, why are identities useful? Because they allow us to help simplify or rearrange expressions. So by definitions, since the two sides are equal, they can be interchangeable. So anytime I see a 1, I can replace it with 5/5, or 2/2, or 49/49. I can replace it with whatever I want. And that's the whole reason why identities are so really cool. So a trigonomic identity is simply an equation that holds true no matter what you plug in for the variable. But trigonomic means it involves sine, cosine, tangent, blah, blah, blah. So we're going to learn about the foundation one. There's quite a few of them that we're going to go over in this video, but they're really, really important. So again, there are several different identities. Today we're going to focus on the foundation ones, the main ones. And you're going to be like, wow, there's a lot of them, aren't there? Well, yes, there are, but there are thousands more. These are just the building blocks, the main ones that could be used for any other future ones. So again, statements that are true for all input values. In trigonometry, input values are angles. So it doesn't matter what angle you plug in, you're going to get a true statement every single time. Now, before we reveal, the big reveal today, all these cool, amazing fundamental identities, I want to make sure you understand where they all come from. They all come from essentially the unit circle, right? When you're on the unit circle, you have the initial side, everybody starts right here, and then we rotate and we create an angle when we rotate. Okay, there's that angle. And where we stop is a point, x comma y. And we understand trigonometry through this scenario because we could easily make a triangle by doing this right here. And we know the height of that triangle, or the opposite of this angle, is y. And the adjacent side is x. And the hypotenuse, well, we know is 1. It's technically r, but, in the unit circle, it's 1. So again, we get this idea, right, that sine of theta equals y. Opposite over hypotenuse. Well, y over 1 is just y. And cosine of theta equals x. Adjacent over hypotenuse. X over 1 is just x. And tangent of theta equals y over x. Opposite y, adjacent x. And then we have the reciprocal ones where we have cosecant, CSC of theta equals 1 over y. Secant of x equals, secant of theta, I'm using the angle theta here. Secant of theta equals 1 over x, just the reciprocal. And cotangent of theta equals x over y. Okay, so every one of the identities that we're going to learn today stems from this information. And the one more thing I want to point out, there's one more way, right? So the trigonometry connects the angle x and y. Trigonometry is this amazing thing that connects the angle x and y of any point on the unit circle. But there's one more way that x and y are connected, and that is using Pythagorean's theorem, because that is a triangle. So x squared plus y squared, the two legs, each squared add together equals the hypotenuse squared. Well, that's just 1 squared, and 1 squared just 1. So this is the other way that we know that they are all connected. And through all of these values, we are going to learn the foundation, the fundamental trigonometric identities. So here we go. The first ones are known as the reciprocal identities. So here are 6 fundamental identities. These are pretty much the easiest ones. These just confirm that sine and cosecant are reciprocals. So 1 over cosecant is sine, and 1 over sine is cosecant. Now, if you're trying to figure out, how the heck do I know that? Just go back to what I've already taught you, right? Think about this, ready? Sine of theta equals y. If I flip this over, y is 1 over y. Well, if I flip the right side, I got to flip the left side. And 1 over y is cosecant. Boom! Cosecant equals 1 over sine. Awesome! Amazing! How cool is that? That's where we get this identity from. And every one is essentially just like that, right? So they're all very, very, very simple to use. Or again, if you want to think about, how do I prove this first one right here in reverse? Just say, well, okay, I know that by definition, cosecant is 1 over y. And if I do 1 divided by 1 over y, but I don't like dividing by fractions, so I'm going to multiply by the reciprocal, y over 1. Oh, that's just y. But wait a minute. Y is sine. Hence, sine is 1 over cosecant. And again, that's true for all of these, right? I mean, think about cotangent. Cotangent is x over y. But if you do 1 divided by that, that's 1 times the reciprocal, y over x. But wait a minute. Y over x is tangent. So again, all of these reciprocal identities come from the idea of the reciprocals, right? They're all very, very simple. It's all just basic substitution. You don't even have to memorize these, just know them. And most kids just start to kind of catch on. Sine and cosecant reciprocals, cosecant and secant are reciprocals, tangent and cotangent reciprocals. So anytime you see a sine, you can replace it with the 1 over cosecant. Anytime you see a cosecant, you can replace it with 1 over sine. So whatever you want to do. That's the coolness of these identities, is that once they're established that they're equal, you can always replace one side with the other wherever you see it. All right, 2 more identities coming straight at you. These are known as the quotient identities. And these are really easy to understand as well. Tangent equals sine over cosine. And let's make sure we understand that. Well, remember, sine is y, according to the unit circle. Cosine is x, according to the unit circle. So if I do y divided by x, sine divided by cosine, wait a minute, y divided by x is tangent. There we go. Same thing with cotangent, right? Cosine's x, sine is y. X divided by y, that's cotangent. You're just using those basic definitions. Okay, it's really, really, really simple. Now, keep in mind here that, I love being on the unit circle. Being on the unit circle is awesome, r equals 1. But even if you're not on the unit circle, this still works, right? Because if you're not on the unit circle, sine is y over r, cosine is x over r. And if I take sine, y over r, and divide it by cosine, x over r, and I say, well, I hate double fractions, so I'm going to take the numerator, and I'm going to multiply it by the reciprocal of the denominator. Check this out, the r's cancel, and you still get y over x, which, guess what, is tangent. So even if you're not on the unit circle and you have a radius value of anything other than 1, it's still going to cancel out, and you're still going to get y over x. So these are two more great, often used identities. So anytime you see a tangent, listen, you're more than welcome to leave it a tangent, but now you could also replace it with sine over cosine, because this is true no matter what. No matter what. All right, let's look at three more, and these three more, I'm actually starring them because they're so important. These are known as the Pythagorean identities. I'm going to explain to you where they come from in one moment. So the first main one is sine squared plus cosine squared equals 1. Now remember, order of addition doesn't matter, so feel free to say cosine squared plus sine squared equals 1. It's the same thing. Now, where do these come from? Well, remember the other way that we can link everything together in a unit circle is by using the Pythagorean theorem. We know that x squared plus y squared, those are the two legs of that triangle, equals the radius or the hypotenuse squared. Well, 1 squared is just 1. But wait a minute. We also defined that cosine of theta equals x. So that's actually using an identity, meaning I could replace this x with a cosine of theta. Now again, the square is still there. I'm only replacing the x. That means the square is still there. Same thing with the y. We know that sine of theta equals y. So I can replace that y with a sine of theta. Don't forget the square. I'm not replacing the square. I'm just replacing the y with sine equals 1. And I get cosine squared plus sine squared equals 1. Now, real quick here, note on why the square is different, right? This is how it should officially be written, right? I like the parentheses. To me, that's very telling. It says, hey, you need to figure out what cosine is first, then square it. But mathematicians are lazy, and they don't like taking the extra time to draw parentheses. I know, that was just so much time to do that. So they thought first, well, if we just write this, if we don't put any parentheses at all, then technically order of operations says square theta first, then find cosine. And that's not what we're wanting to do here. So they said, you know what, we don't want to do this. Even though this makes more sense, cosine inside the parentheses gets done first, then square the result. They said, you know what, again, writing parentheses is way too much work. Unbelievable, right? And they said, well, listen, why don't we put the square right here after the cos, then the theta. And this is their way of writing cosine, pause, squared, without the parentheses. So that's how we write it right here. But once again, notice how I have the sine squared first. It doesn't matter, right? Order of addition doesn't matter. So I can have sine squared of theta plus cosine squared of theta equals 1. Now, it's super important that you understand that these three rules right here, and I'm about to talk about the other two, these three rules only work if it's squared. Like sine cubed plus cosine cubed does not equal 1, right? Sine to the fourth plus cosine to the fourth does not equal 1. They only work for squares, right? It's got to be this or nothing. Now, where do these next two come from? They actually come from just doing a little bit of algebra. So imagine I start with this top function, this top identity, excuse me, this top identity, sine squared plus cosine equals 1. And I do a little of algebra, right? Algebra means just do everything the same and you're okay. So imagine if I divide everything by sine squared. Again, remember, rules of algebra say as long as you divide everybody by the same value, you're technically not changing. You're changing how it looks, but you're not changing the value of it. So again, sine squared divided by cosine squared is 1 plus cosine squared divided by sine squared. Now, what's that? Well, essentially, cosine squared is cosine times cosine. And sine squared is sine times sine. So therefore, I have cotangent, using the quotient identity. Cosine divided by sine is cotangent. So I have cotangent times another cotangent, because I got cosine over sine, that's a cotangent, times cosine over sine, that's another cotangent. So that's how we get cotangent squared. Equals, now check this out, 1 over sine squared. Well, wait a minute. That's 1 over sine times 1 over sine. All right, hence 1 over sine squared. But wait a minute. Look back up here. 1 over sine is cosecant. That's one of the reciprocal identities. So I could write cosecant theta times cosecant theta. Sorry, that looks messy. And cosecant times cosecant is cosecant squared. So that's where this other identity comes from. It's simply taking the main identity and dividing everything by sine squared. Really simple, but it does create a new identity, which we love. But again, this identity only works if there's squares. All right, now where does the other one come from? Actually, the exact same process, but now we're going to divide everything by cosine squared. Now remember, as long as you divide everybody by the same value, you haven't really changed the equation. You haven't changed the fact that it's equal. You just change how it looks. Now, sine squared divided by cosine squared. Well, remember, sine divided by cosine, that was one of our quotient identities. Sine divided by cosine is tangent. But I got sine over cosine times another sine over cosine because of the squares. So that generates tangent squared of theta. Cosine squared divided by cosine squared is just 1. And then 1 over cosine squared. Well, remember, reciprocal identities, 1 over cosine is secant. So that would be secant squared. Again, 1 over cosine is secant. 1 over the other cosine, because again, it was cosine squared, cosine times cosine. 1 over secant times 1 over secant is, well, secant squared. All right, so that's where we get the other identity from. Now you say, well, wait a minute, it says 1 plus tangent. It's addition, guys. Addition can be done in any order you want. Doesn't matter. So there is that other identity. So these three identities are I would actually probably say the most common used. I mean, but they're all used a lot. But these are some really, really important ones. So again, I want to emphasize that these three are only true with squares, right? It's like Pythagorean's theorem. A squared plus b squared equals c squared only works for squares. It's not true for a cubed plus b cubed equals c cubed. So again, got to be squares. But since all of these other identities, the quotient and the reciprocal, don't involve addition or subtraction, then technically they would all work for any power. So cosine cubed equals 1 over secant cubed. Tangent to the fourth equals 1 over cotangent to the fourth, right? It's just multiplication, so that's fine. Same thing here. Cotangent to the fifth would equal cosine to the fifth over sine to the fifth. So these ones work for multiple powers, whereas these ones only work for squares. All right, couple more identities to throw at you here. These ones are called the cofunction identities. And these ones can be a little bit confusing, so I'm going to do my absolute best to explain them. Imagine we have a right triangle, and I'm going to call this theta. Now, what do you know about this angle right here if I'm calling this top angle theta? Well, I don't know it, to be honest. I mean, I don't know a number, but I do know that all the angles of a triangle add up to 180. And this one is already accounted for 90 degrees, so that's half of 180. So that means the remaining two angles have to add up to 90. So if I know that this angle right here is theta, then this angle down here would be 90 minus theta. So I still don't know what it is, but at least I know what it is in terms of theta. Now again, remember we like to use radians. So 90 degrees is equivalent to pi over 2 radians. So again, pi over 2 minus theta would be that angle right there. All right, now let me label some sides here. So let's call this side M, this side G, and this side P. Those are my initials, MGP. Okay, so if I say, hey, what is sine of theta? Well, you would say, duh, opposite M over hypotenuse P. Wow, this is easy. But imagine if I said, okay, what is cosine of pi over 2 minus theta? Now, don't let this confuse you. Pi over 2 minus theta is just this angle. Unfortunately, I don't know exactly what it is. But again, I'm not trying to make this overly complicated. Pi over 2 minus theta is just an angle. If I knew what theta was, I could subtract and I would get the angle. But again, I have that picture drawn right here. So cosine of pi over 2 minus theta is adjacent M over hypotenuse P. And guess what I just realized? That sine of theta is M over P. And cosine of pi over 2 minus theta is also M over P. So I guess they're equal. And that's exactly where we get this one of the cofunction identities from, right? So these are true. It's an identity. Sine of an angle equals cosine of pi over 2 minus that angle. And again, it literally comes directly from the right triangle, where if we label one angle theta, the other opposite angle automatically equals pi over 2 minus theta. Or again, 90 degrees if you like, minus theta. And again, we know that when you switch angles, the opposite and the adjacent switch. So therefore, sine would be m over p, whereas cosine of the other angle would also be m over p. And again, I could use the same logic to repeat and understand the rest of these identities. I'm not going to waste your guys' time, but hopefully you can understand how simple that is. Let's just do one more, right? Let's talk about cotangent of theta. Cotangent of theta is adjacent over opposites. That would be g over m. Awesome. But what about tangent of pi over 2 minus theta, the other angle? Well, from this other angle's perspective, cotangent is tangent is opposite g divided by adjacent m. So what did I just show is that cotangent and tangent of pi over 2 minus theta are exactly the same value, hence what we got right here. All right, so hopefully that one makes sense. At the end of the day, I don't really mean this, but I tell kids, listen, hopefully you understand what I just talked about there, but even if you don't, guess what? Just have these written down, that way you know the cofunction identities. I hate saying that, but it's really true. All right, one more set of identities. These are called the odd-even identities. Now, I don't want to go back and reteach a lesson in Algebra 2, but in Algebra 2, you should have learned about even function and odd functions. Essentially, even functions are functions that if you plug in a number and you plug in the opposite of that number, you'll get the same value. For example, if I plug in 3 to a function and I plug in -3 to that same function, I get the same value. A very simple example of that is x squared. 3 squared is 9, -3 squared is 9. So regardless if I plug in 3 or -3, I get the same result. They're equal. 3 squared equals -3 squared. They both equal 9. That's considered an even function. There are only 2 even functions in the world of trigonometry, and that is cosine and secant. And again, to easily explain this, just take a look at the unit circle here. So let's actually give an angle like 90 degrees. So if I do cosine, let's do 30 degrees, sorry. Cosine of 30 degrees. Cosine of 30 degrees is right here. Here's 30 degrees. And cosine is radical 3 over 2. Easy. Awesome. Okay. But what about cosine? And again, the only change I'm going to make is instead of 30 degrees, I'm going to do -30 degrees. Well, check this out. -30 degrees is right here. It would be coterminal to 330. -30 degrees just straight down. And guess what? Its cosine value is also radical 3 over 2. So whether you go positive 30 degrees or -30 degrees, the x value, cosine, doesn't change. It's the exact same. And since cosine and secant reciprocals, the exact same idea would be true for secant. Now, odd functions are slightly different. Odd functions is when you plug in a number and then you plug in the opposite of that to the same function. You don't get the same number, you get opposites. So for example, imagine I were to plug 4 into a function and I get 9. If I were to plug in -4, I would get -9. Now again, remember, even functions, if you plug in 4, -4, you get the exact same thing. You get the same exact value. But an odd function is if you plug in 4, you get an answer. If you plug in -4, you get the exact same numerical value, but negative. That's the definition of an odd function. Again, you should have learned about in Algebra 2. Don't want to spend a ton of time on it. And that's true for sine, cosecant, tangent, and cotangent. So for example, let me explain sine. If I do sine of -60 degrees, what happens? Well, -60 degrees is down here. Right here, it's coterminal 300. Sine would be negative radical 3 over 2. Okay, negative radical 3 over 2. But if I plug in 60 degrees, positive 60 degrees, positive 60 degrees is right here, and its sine value is radical 3 over 2. Now, those aren't equal, but again, that's the whole point of the negative sign right here. If I tag on the negative sign, then they are equal. And that's an odd function, is just tagging on a negative sign out in front would make them equal. And again, same concept. As I mentioned earlier, I really can't believe I'm saying this, but I truly hope you guys understand these identities. But at the end of the day, you kind of just need I don't even have to say memorize them, because you can have them written down on a cheat sheet. So at the end of the day, these are the fundamental identities. The reciprocal identities, write them down on a cheat sheet. Quotient identities, write them down on a cheat sheet. Pythagorean identities, write them down on a cheat sheet. Cofunction identities, write them down on a cheat sheet. And finally, the even odd identities, write them down on a cheat sheet. I allow you to use a cheat sheet. Please use it. That way you have all these identities right hand. Now, the big question moving forward is, what are we going to do with all these identities? Well, we're actually going to do a lot with them. We're going to evaluate trigonometric values. We're going to simplify, simplify, simplify. And I say it 3 times because we are going to do a lot of simplifying. That's really the big purpose of identities, that they allow us to simplify trig expressions to things that are simpler and easier, which we love. We could also prove or verify other trig identities. Okay, that might be weird, but you're actually going to love it. I think it's quite easy. And then we're going to use trig identities to help us solve trigonometric equations. So the next couple videos after this one are going to go over all of these ideas, using the fundamental trig identities to help us further our understanding of trigonometry through evaluating, simplifying, proving or verifying, same thing, and trigonometric equations. So can't wait to dive into it. See you in the next video.